I'm Everett Whitaker, here today to give you a short little discussion about the EPA environmental regulations, the Clean Power Plan, and to talk to you a little bit about the tools and services that we can provide to help decision makers and policymakers understand the rule and its impacts and how they can go about determining the best course of action. I'm part of GE Energy Consulting. It's a group of about 100 engineers and economists. We're here to help GE set policy, determine where to invest, and to help people outside. We do a lot of work with utilities, with utility commissions, and increasingly states. Who is Energy Consulting? We're really made up of three groups, largely. The Power Economics Group does the long-term planning. What's the right thing to build, where to build it, that kind of thing. What's your investment return going to be like? In the middle, Power Systems Operations and Planning. Those are the people that once you decide what you're going to add to a power system, they're the ones that help make sure that those new components, generators, whatever, get added to the system and make the system better. Don't make the system worse. Make sure the system will be able to ride through any perturbations through time. And then finally, Global Power Projects is another group we have that once you put a generator into a specific place, you have to prove that that generator will do what it should do to meet codes and demonstrate that it won't do things that it shouldn't do. To do all that work, we have a suite of large software that helps us. It's called the Concorda Suite. It's made up of three major parts. GE Maps is a production simulation tool. Helps us look at entire power systems, the generation, the transmission, how those all work together to keep the lights on every day. When you get down into small time increments and dynamic events, plants tripping offline, transmission lines failing, then we use something called PSLF. It looks at very short time increments and helps decide whether voltage and frequency will move and be, or not move, and be taken care of to the point where the lights stay on. Then finally, Mars. Longer term, if you're looking around and you say, how can my system evolve, or how will it evolve, and will that system then be kept stable, operating efficiently, keeping the lights on? Mars is the program we use for that. Today we're going to talk mostly about work that was done by Power Economics in this case. We're looking at the draft Clean Power Plan. It's the way it was put out by EPA last year. Work we did, and we're just using this as an illustration of the kinds of tools and capabilities that can be brought to bear on problems that you might have. We did this work based on a long history, over 100 years of being in business, with I think it's about 1,000 hours of people experience that are on the staff. We do power market assessments, investment decision analysis, variable generation studies. The variable generation studies are a big area of business for us right now. As you all know, a lot of wind, increasing a lot of solar going into power systems around the country and Canada. And we've been doing a lot of those big studies, helping people understand how much can be put in and what the impacts of those new types of generation are going to have on the rest of the system. Integrated resource planning, another one for both utilities, for state agencies and such. What's the right way to build out the power system? What should I be doing in terms of new generation, beefing up transmission, that kind of thing? Integrated resource planning is one of the things we do, and it helps people come up with the optimal way to meet everyone's needs. And then finally, the discussion point for today is environmental regulations. With all the regulations that have been promulgated in the last 10 years, a lot's been happening, but now we have the Clean Power Plan. It's going to make a lot more happen. And we'll talk a little bit about what some of the things that could happen, the tools that can help you figure that out. This slide just discusses the three tools I mentioned before. As you go through that, the way basically most people enter it is right in the middle. You're looking at long-term effects, trying to figure out what's the right thing to add for my system. If load grows, what kind of generation is the optimal thing to put in? You can get to those kinds of answers with maps there in the middle. From long, or like 1 hour increments up to 10 years, typically we run with GE Maps. And what that does is it simulates power systems, all the generation, all the transmission, really how those things work together, and when they can't, when they're limited by transmission limitations, that kind of thing, how's the system going to deal with it just the way a grid operator would do it. And then if you determine with a long-term analysis you have some optimal build-out, some way the system is going to evolve, one of the things you need to do is look at very small time increments. What happens when something goes wrong? When there's a single generator trips out or a line, you use PSLF to make sure the voltage transients and or the frequency, those stay in a range that the system can cope with, or it'll identify where they don't, and you have real problems that need further solutions. And finally, the MARS simulation package is what we use for like the NPCC here in the Northeast to help determine what the long-range reliability is going to look like given the build-out and the potential retirements that could happen. How's that going to affect overall annual loss of load expectation? For today, we're going to talk about the 111D, which is part of the proposed Clean Power Plan. It's the part that was dealing with existing power plants. And we're picking that just as a small part of a study we did last year, just to illustrate some of the questions that were asked and some of the analysis that was done to get answers. For those who aren't very familiar with the Clean Power Plan, this shows that they had state goals in the plan. The EPA came up with it using this equation at the top. They came up with rate goals that they were trying to get for each state to get an overall reduction for the U.S. of carbon down to 30% from 2005 levels. So what this analysis is going to do is show you for the 4 building blocks they had in the draft rule. One of those was how could I improve my fossil plants, which is improving either the generation down at the bottom or the amount, or reducing the amount of carbon in the top of that equation up there. So the small part of this study that we're going to talk about today is the heat rate improvement building block. It's one of 4 in the draft rule, and you'll note down on this slide, this talks about 3 blocks that's really talking about what ended up in the final rule. Okay, what did we do? We went through 5 steps looking at, again, this is just 111D, the existing plants. How could you fix those plants, make improvements either in the operation of them or physically in the plant to get more generation for less carbon? So basically improving efficiency. The thing we did was we went through and looked at the entire fleet, and this is one of the luxuries we have in energy consulting is it's not just us. We have 100 people in our group, but we have all of GE to draw on. And in this case, we're able to draw on GE Power Generation Services, who has extensive experience in the existing fleet of fossil-fired plants. So we pulled them into the team, and they helped us figure out what's possible. And that's what this chart goes through in quite a bit of detail. 2 things you can do. You can just operate your plant better, and that's the practices part in step 1 and step 2. How can I tighten valves? Can I change the operating profile just to make this plant operate better, just as it is, but I do a better job? And I've seen this happen before where plants can improve 2 to 4% just by doing a better job of concentrating on making them efficient and not wasting energy. Then the other part of this was the upgrades. This is in the middle on this, step 3. And there we went through, and again, exercising or making use of the expertise in GE, we were able to go out and look not just at fleets and what was theoretically possible, but look at specific units and say what had they already done in terms of improving their efficiencies, and then make an assessment of what else could be done. And then finally, we took the results of those steps and said, if we know what is possible for each, let's put those into a program that we license called NEAM, where we go out and simulate all those improvements and see what the effect is on overall carbon reductions. And the results of this. You can see we've racked up by heat rate and the amount of carbon there that each of these categories of plants would emit. And you can see up at the top how much gain you'd get in heat rate improvement. And what is striking to me is that you don't get that much. It's 2% to, well, the high was 7% for some plants, but down to 2.5%. At this point in time, the EPA's goal was 6%, and this work was basically showing you couldn't get there. And in fact, through all the rulemaking process, the rest of the country was able to convince the EPA that that 6% target of theirs built into their analysis was a little too high. They reduced it, and now it's a smaller number, and it's based on regional averages, not some higher level 6% value. The bottom line, this is a kind of answer that you can get from all this analysis. You get who and what can do what to help you meet your policy goals. There's another view of it. You can see from this analysis how many megawatts did we expect would retire economically. Who could make upgrades? That's another part of the analysis. Who could make upgrades and who wouldn't survive the process? So there again, what's the goal of all this? It's how much of the overall carbon reduction goal can be met by improving your coal fleet. Some of the plants just can't do it. They're going to retire. Well, if you replace it with something cleaner burning, that's going to help your CO2 goal. So it's an important input to the overall decision process. So moving from the draft rule onto where are we now, and what can these tools do for you? One of the big changes in the final rule is reliability impacts. Several interveners or commenters on the draft rule pointed out that with all the retirements that were being forecast, that the system might not hold together. So the EPA basically punted that ball to the states, and that's where something like MARS is going to be helpful to some people. There are a few other programs out there, but we have real good we're very satisfied with MARS, so we're expecting to do a lot of work in this area. Basically, go out and say, given the retirements that you forecast, is your state, is your utility, is it going to be reliable? This is a nice chart that shows the overall plan. At the top, we're using maps. You simulate the system through time, and you get the energy revenues, capacity payments that go in, both for, you can do it for individual plants, you can do it for utilities, you can do it for the entire fleet across the state. And you get all the cash flowing in, the various costs that are pulling cash out, and from that, at the far right, you can see the amount of money they get, and then make the assessment of whether individual plants are going to retire or whether they're going to survive, whether they can afford to do the upgrades that you're assuming in your analysis. Once you do that, and as you saw in that prior chart, quite a bit of retirements, can the system then hold together? You start retiring more units. The transmission system depends on generators to hold up voltage around the system. If you're retiring those, the transmission system needs support or loses support if those big generators are gone, and that changes the amount of power that can flow. And you need to look at that with something like PSLF. Dynamically, can you get the power where you think it's going to go? And finally, with MARS, with all those changes, both in new additions of new generation types and the retirements of some of the coal fleet, long term with a Monte Carlo process, will your system be able to keep the lights on?